So number 87 from last night's homework. If f of theta is equal to sine theta, so we have a function that's defined to be sine, and if that equals 0.1, find f of theta plus 1. Sorry, theta plus pi. So what happens if I add pi to that? So sine of theta, f of theta is equal to sine theta, which equals 0.1. What's f of theta plus pi? Well, f of theta plus pi is just equal to sine theta plus pi, right? And so if sine theta is equal to 0.1, so let's go ahead and think about this visually first of all. All right, let's go ahead and draw our unit circle. And let's just say that theta is this angle right here, okay? Now, if I were to go ahead and add pi to that, pi is 180 degrees, right? So theta plus pi is going to put me over there, right? So that's 180 degrees, and so now I'm down here. And because of that, geometrically, the reference angle is going to be the same, right? If I add pi to it, do we see that? We have vertical angles there. So as a result, those angles have to be equal to each other. And so if we think about it, so here's my point in the unit circle right here, and here's this point here. We know that the y coordinate at this point is 0.1. We don't know what the x coordinate is, but we do know that the y coordinate is 0.1 if sine theta is equal to that. So the y coordinate of this point has to be what? Negative 0.1, right? It's got to be the opposite. So we should get negative 0.1 for sine of theta plus pi, based on what we know about the unit circle and just basic geometry, because we know that these reference triangles are going to be congruent, right? Because we have side, angle, side, or sorry, angle, side, angle, rather. Actually, what do we have? We have angle, side, we have angle, angle, side, yeah, AAS. They're congruent by AAS. Okay? And that makes all the sides the same length, so that means that this side has to be the same length as this side, and bing, bang, boom. The topic of discussion today are going to be properties of the trig functions. We're going to develop some of the basic, what we call the fundamental identities, and just talk about all the different properties the trig functions have before we get into graphing them tomorrow. And so the first thing we'd like to talk about, actually the first thing we should do is just let's go ahead and list off all the definitions of the trig functions that we established yesterday based on the unit circle. So here's our unit circle, and here's some angle theta being opened up, and the point that the terminal side intersects the unit circle, we'll just call the point xy. And so the basic definition, sine theta equals y, cosine theta equals x, tan theta equals y over x, secant theta equals 1 over x, cosecant theta equals 1 over y, and cotan theta equals x over y. Right. So those are all the definitions that we're working with today. And what's important to know for tan theta and secant theta In both cases, this is going to be important in a second, x cannot be equal to 0 because it's in the bottom. And in the case with cotan and cosecant, y cannot equal 0 in both of those instances right there. And so let's just start off by looking at domain and range of sine and cosine. Okay, domain and range of sine and cosine. So, first of all, is there any value of theta that we can't plug into sine and cosine? Because usually we determine the domain of a function by figuring out what things aren't in the domain, then whatever's left over is the domain, right? So the first question we ask ourselves, is there any real number that I can't plug in for sine or cosine? And when I say can't plug in, I mean a number that will result in giving us a non-real answer for sine theta or cosine theta. Or is there any value of theta good? Any real number theta? Based on our understanding here. Well, I mean, we know for sure any, number between 0 and 2 pi is good, but then I can just keep going for as many revolutions as I want. So, and then negative values are good too. I could rotate in a negative direction, and then any negative angle we can find sine or cosine for. So really, that's all real numbers, right? And that's going to be true for sine and cosine. So the domain of both sine and cosine is all real numbers. The range, on the other hand, what is the range going to be? Well, let's think about this. What's the biggest and smallest that, let's look at sine, for instance, as I travel around the unit circle. When I'm at 0, what is sine?
No sine.
Sine is the, which coordinate?
Sine will be 0.
Sine 0, so sine goes down to 0, it goes around here. What's sine up here?
1.
So it goes from 0, it increases slowly to 1, then it starts going back down, right? And what is sine right at 180 degrees?
0.
And then it goes negative, right? Because it's below the x-axis and it's the y-coordinate, and it gets down to,
-1.
and then it comes back up to,
0.
and then it repeats that over and over again. So what's the range? What are the possible values that sine spits out? What's the smallest value?
-1.
Largest value?
1.
And everything in between, right? So the range is -1 to 1. Right, so and that's true for cosine as well. We can think of it the same way. Cosine starts at 1, goes to 0, down to -1, to 0 again, then back to 1. So it does the same thing. So the domain is all real numbers and the range is -1 to 1. Okay, so that's pretty straightforward for sine and cosine. That's not really a big deal. Now the question is, for the functions that involve fractions, it's going to be a little bit more complicated because, look at that, we have stuff in the denominator that's possibly going to give us divide by 0 issues. Well, we know there's definitely angles that pose that problem for us. So domain and a range of tangent. Right, so first of all, the domain, that's probably the easier part. Right, tangent is equal to y over x. And so I'll go ahead and draw my unit circle again. And so anytime x is equal to 0, that's not good. That's going to return a non-real value for tangent of theta. Right, so where is x 0? What values of theta is x 0? Well, it starts off at 1, then it goes to 0 at what angle is this that it gets to 0 at?
90.
Pi over 2 or 90, yeah. And then it gets back to 0 at 270, which is 3 pi over 2. Right, so pi over 2, 2 pi over 2, and then it's just going to repeat that over and over again. So pi over 2, so 1 pi over 2, not 2 pi over 2. 3 pi over 2, not 4 pi over 2, 5 pi over 2, not 6 pi over 2, 7 pi over 2. So are we seeing that it's going to be odd multiples of pi over 2? So the domain for tangent is going to be all real numbers except odd multiples of pi over 2. So 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Those are all going to put you on the y-axis, which means that x will be 0. The range, that might be the trickier part here. What's going to happen with the range here for tangent? What's the smallest that tangent can be? So this is the trickier one for sure. Thinking about the range of tangent.
Well, it goes to 0, but it can't be 0. Or -1, I mean.
Could it be 0 though?
It could be 0, yeah.
Yeah, it could be 0. So what's going to happen here? Tangent starts off at 0, right, because the top is 0, and then it slowly is going to increase, because what's happening? X is getting smaller, and y is getting larger until we get a situation where it's undefined, right? So it's growing, growing, growing. Why is it undefined right there? It's undefined because we have this is similar to the rational function which we just saw. What's going to happen right there? Because the bottom is blowing up as the top is getting really small. Sorry, the top is getting really big as the bottom is getting really small. We're dividing by a smaller and smaller number. It's going off to infinity, yeah. So it's going to go from 0 all the way to infinity right here. Right, because it's going to have a vertical asymptote at those odd multiples of pi over 2, as we'll see in the graphical version of the function in a little bit. And then as we go over here, now all of a sudden one of the two variables is negative, right? The x variable is negative. The y variable is still positive, so tangent becomes negative over here in the second quadrant. And it's a really, really big negative number at first because x is really, really small, negative, right? And y is really, really, well, it's not big, but the more important point is that x is really small, negative. So so what happens is we immediately switch to negative infinity, just like a normal vertical asymptote. And we come down from negative infinity all the way to 0. And then from 0, now both of them are negative, so it's positive, and it's going to increase all the way up to positive infinity again as x goes down to 0. The bottom blows up, but the top, and they're both negative, sorry, so it should go to positive infinity. And then it's going to immediately switch over to negative infinity and then go back down to 0 again. So the range is going to be, goes from 0 to positive infinity and also 0 to negative infinity, depending on which quadrant you're in. So it hits everything between negative infinity and positive infinity, right? So all real numbers. So even though its domain is missing some values, multiples of pi over 2, its range is not. And then cotangent is going to be the same general idea, right? Except cotangent theta is going to be equal to x over y, so it's going to have, its domain is going to be what? It's going to be undefined when cotan is going to be undefined when y is equal to 0, which is going to occur at 0, and then at pi, and then at 2 pi, and at 3 pi, 4 pi. So multiples of, or just multiples of pi, right? 0 pi, 1 pi, 2 pi, 3 pi. So all real numbers except multiples of pi. And the range, it's going to do the same thing, isn't it? It's going to be undefined at 0, and then it's going to slowly climb down from positive infinity all the way to 0. And then it's going to become negative, and then go all the way down to negative infinity as we approach 0 in the denominator right here. And then it's going to be, they're both going to be negative, so it's going to come down from positive infinity to 0, and then go back up to go back down to negative infinity there. So it's going to hit all real numbers as well. This will make more sense graphically, of course. Okay, so all real numbers. Now let's think about what's going to be happening to, so domain and range of secant whoops, not cosine. Cosecant, so secant theta, which is equal to 1 over x, right? Make our unit circle. And we think about what's happening to x. We start at x being 0, oh, sorry, x being 1. Right, so it starts at 1, and then what happens? Because it's 1 over 1, because x is 1 at this point. And then x is decreasing, so it's getting bigger or smaller?
Smaller.
The denominator is decreasing, though.
Oh, so the number is getting bigger.
Bigger, 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 until it gets to 0, which means it's undefined at 0, right? Because we're dividing by 0, so it's just going to get bigger and bigger and bigger and blow up to infinity. And then it's immediately going to be negative infinity because we're going negative, and it's going to come down from negative infinity to 0, right? Sorry, to 1. So it's to negative 1. It's going to come down from negative infinity to negative 1, and then it's going to go and immediately start blowing up again and going towards negative infinity. And then we jump to the other side here, and x is positive again, so it's going to become positive, but it's also going to be really big, so it's going to come down from positive infinity to 1. So from 1 to positive infinity, right, and then negative infinity down to negative 1 back down to negative infinity, and then positive infinity back to 1. So what numbers are not part of the oh, I should, first of all, the domain, I'm looking at the range there. The domain is just like tangent, right? All real numbers except anything that's going to make x negative, which are odd multiples of pi over 2. And then the range, well, the range, we hit all the numbers between 1 and positive infinity, all the numbers between negative infinity and negative 1, and that's it, right? Do we ever hit any numbers between negative 1 and 1? Is there any way to get a number that's less than 1 and greater than negative 1 by taking 1 over x here?
No.
There isn't, is there? So all those numbers between negative 1 and 1 are not part of the range. But anything 1 or larger, or negative 1 and smaller, is. So all real numbers except all the numbers between negative 1 and 1. Right? And the same general idea for cosecant theta. It's 1 over y. The domain is going to be a little different just because it's 1 over y instead of 1 over x. That just means that the domain is going to be anything that's going to make y 0, which are multiples of pi. So all real numbers except multiples of pi. And the range is going to be the same thing, all real numbers except everything between negative 1 and 1. Because it's going to have the same general behavior. All right, so domain and range of, that covers domain and range for all 6 of the trigonometric functions now. So, one thing that is true about all of our trigonometric functions here is that they are, so trig functions are periodic. Meaning they repeat. So the question is, what is the period of our trig function? So for sine theta, right? I'm going to go back to the unit circle for the umpteenth time here because it's all based on the unit circle. Whoops.
Unit oval.
What?
I said unit oval.
Yeah. Oh. All right. Good enough. All right, so sine theta. How often does it repeat? Well, let's think about what's happening to it. It starts at sine theta is equal to y, right? So how often does the y coordinate repeat as you go around the circle? Right, you start at 0, you go up to 1, you go down to 0, and then down to -1, and then back up to 0 again, and then you repeat that whole process again. So really it repeats every full cycle, right? We do hit some repeat values in between here, like we start at 1, and then we go up to, we start at 0, and then we go up to 1, and then we go down to 0 again. So we hit the values between 0 and 1, we repeat in there, but we don't actually repeat the full cycle until we get all the way over here, because then we do all sorts of other stuff. We get down to the negative numbers here, and come back up to 0 again, right? So it takes a full cycle to really repeat that behavior, and then we do the same thing over again, and the same thing over again, and the same thing over again. So for sine, and the same thing's going to be true for cosine, right? So the period of sine and cosine and because cosecant and secant are just reciprocals of sine and cosine, they do the same. They also repeat every 2 pi. Any function based on a function that's periodic has the same period. So secant and cosecant, sine, cosine, secant, and cosecant all have a period of 2 pi. They repeat every 180 degrees, or sorry, 360 degrees. Right. Now, on the other hand, tangent's a little different. It's sort of the odd man out in this case. It's equal to y over x, right? And let's think about what's happening to tangent. Well, tangent goes from being 0 up to positive infinity, and then negative infinity, because we get over here and the x-coordinate is very, very small negative on the left side of the y-axis here, and the y-coordinate is right around 1. And so it's at negative. It's sort of coming down from negative infinity all the way to 0, and then it goes all the way back up to positive infinity again, and then down from negative infinity to 0. So really, it does the same thing from 0 to pi as it does from pi to 2 pi. So it doesn't take a full 2 pi to completely repeat its entire behavior. So it does one full cycle to pi, another full cycle, another full cycle, another full cycle. Once again, from 0 to infinity, from negative infinity down to 0, from 0 to infinity, from negative infinity down to 0, and so it repeats every pi. So period of tangent, and by connection cotangent as well, since it's based off of since it's the reciprocal of tangent. So period of tangent and cotangent is pi. So knowing the period is important, and so that means that there's some important properties that stem from that, right? So first of all, an important property is, for any periodic function f of x, where the period is p, or with a period of p. Just erase all of this. Let's try that again. So with a period of p, it's true that f of theta plus the period is just equal to f of theta, right? Because by adding p to theta, it means that I've gone an entire additional full cycle away from theta, meaning I'm going to get back to where I started. Right? If I go a full cycle from a starting point in a periodic function, I should end up at the same place that I started at. So that's why f of theta plus p is always going to be f of theta, right? And this is called the fundamental period. And this is the smallest number for which this is true. Because, so the fundamental period is the smallest number for which this is true, because any multiple of p, the same thing's going to be true. If I add 2 pi, I'm going to go, like for instance with sine, if I add 2 pi, I'm going to go all the way around the circle. If I add 4 pi, I'm going to go all the way around the circle twice and end up at the same point. So any multiple of the period is also going to get you, back to where you started. And so that gives rise, this is true for all periodic functions, and that gives rise to the periodic properties that we have for sine, cosine, tangent, all 6 of them. So the periodic properties of the trigonometric functions says that sine of theta plus 2 pi has to be equal to sine of theta. Cosine of theta plus 2 pi has to be equal to cosine theta. Once again, but because 2 pi is the period of sine and cosine, right? And the same thing is true of secant and cosecant, because they also have a period of 2 pi. And also, and then what will be true for tan is I have to just add only pi, right? And the same thing for cotan. Whoops. Okay. All right, and so these are important because we can use them to determine, what certain values for trig functions are. And we've sort of already been doing this, but we can do this to make it easier to determine the values of certain trig functions. Sine of 17 pi over 4. Right? That's going to be multiple revolutions around the circle, right? But if I can express this as just a smaller number, maybe a number that I maybe know the value for it off the top of my head, and then just add a certain number of periods to that, then it might be easy to compute. So this is fourths, right? So maybe I can express this as pi over 4 plus something. What would this be equal to? Pi over 4 plus how many more fourths to get to 17 fourths?
16.
And what is 16 fourths the same as?
4 pi.
And so 4 pi is a multiple of the period of sine, which is 2 pi. And so this is going to be the same as sine of pi over 4. And off the top of my head, because pi over 4 is 45 degrees, it's one of our special angles, I know that off the top of my head that's equal to the square root of 2 over 2. And if not, I could just make my unit circle and do all that stuff. So we can sort of break that down to a simpler problem, right? You could do the same thing with like cosine of 5 pi. That's just equal to cosine of pi plus 4 pi, right? Which is the same as cosine of pi, because 4 pi is a multiple of 2. And cosine of pi, cosine is the x-coordinate. Pi is 180 degrees. That means it's going to be -1, right? What about like tangent of, let's say, 25 pi over 6. That's one you look at and you go, oh, that's a headache, right? Well, it's not if we break it apart and say, well, this is sixths, right? So what if we do tan of pi over 6 plus we have 24 more pi's over 6, which is 6 pi. Sorry, 4 pi. And so really this is just tan of pi over 6. Pi over 6, we might want to make a unit circle for this one. Pi over 6 is, crap, this looks bad. Pi over 6, what is that in degrees? Anyone know what pi over 6 is in degrees?
30 degrees.
30, yes. So our angle here is 30 degrees. Right, that means the one up there is 60, so we have a 30, 60, 90. So if this is 1, then the side across from the 30 has to be half that. It has to be 1/2. And the other one is going to be square root of 3 over 2. And so my x-coordinate is going to be square root of 3 over 2. My y-coordinate is going to be 1/2. So it's y over x. So it's going to be 1/2 over square root of 3 over 2. And that's going to give us 1 over, whoops. That'll give us 1 over square root of 3, which is going to, if we rationalize it on there, it'll end up being square root of 3 over 3. So we can use this idea of periodic behavior to help us calculate exact values of trigonometric functions more easily than we would otherwise be able to do. Like in the first two cases, you know, if I didn't do it this way, I would have to draw out the unit circle and go ooh, and do as many rotations as I need to, and eventually get to where I need to get to, and then I'd have to think about what's the reference angle and all that stuff. But if I just break it apart like this, then it's really just sine of pi over 4, which is, I know that off the top of my head because that's an easy one, which you should hopefully know that off the top of your head pretty soon as well. And cosine pi is super simple because it's a quadrantal angle, right? And tangent pi over 6. Tangent's difficult because it's y over x. You don't necessarily have to memorize that one. Just remember, if you know what sine of pi over 6 is and cosine of pi over 6 is, then bam. But you are probably one thing you're going to want to remember pretty soon is the unit circle. In terms of, and what I mean by that is all of the values of sine and cosine on the unit circle. If you know sine and cosine, you can find tangent or cotangent or secant or cosecant. So if you know just sine and cosine from 0 to 360, all of the angles that have special angles or quadrantal angles as the reference angle, then these types of questions go a lot faster. Okay, let's look at another idea here, which is in terms of properties of trig functions, the signs of the trig functions in each quadrant. Right. And so for sine theta and its reciprocal, cosecant theta, they're going to have the same signs in the same quadrants because they're both based off the y-coordinate, right? There we go. So let's just go ahead and I'll make my thing. So first quadrant, second quadrant, third quadrant, and the fourth quadrant. So sine theta is just y. Cosecant theta is the 1 over y, so the sign will be the same based on the y-coordinate. What's the sign in the first quadrant? Positive, then it's for y?
Oh, for 2, sorry, I was going the wrong way.
2, yep. And then these are both negative, yeah. Okay, so for sine and cosecant, that's where it's positive and negative. For secant theta and cosecant theta, sorry, for secant theta and cosine, I should say. Let's make the same type of chart. They're both based on the x-coordinates. The x-coordinate is positive, negative, negative, positive, right? And then lastly, for tangent theta and cotangent theta, make a chart for them. Now, this is a little bit more complex for tan theta, it's y over x. So if we have two numbers that are both the same sign, and I divide them, I'm going to get if they're opposite signs, I'm going to get a. So in the first quadrant, they're both positive, so their quotient's going to be positive. In the second quadrant, one is positive, y, and one is negative, x. So the quotient is going to be negative. In the third quadrant, they're both negative, so the negative divided by negative is positive, right? And in the fourth quadrant, x is positive and y is negative, so they're negative. And the same thing will be true for cotangents. It's just the reciprocal of that. Reciprocals have the same sign. Okay. All right. Let's take a quick break. All right, so one type of question you want to be able to answer is if you're told that sine is positive and secant is negative, what quadrants must the angle be located in? Unfortunately, I wasn't recording when we went over this last one, so the answer is already here. But just to explain this, if we know that sine is positive in the first and second quadrants, because sine is the y-coordinate, right? And we know that secant is negative because secant is the reciprocal of cosine, and cosine is negative in the second and third quadrants. All right, and so where both sine is positive and secant is negative has to be the second quadrant, right? Which is where we come up with this solution right here. So, given information about the signs of two of the trigonometric functions, we should be able to figure out what quadrant the angle is located in, even if we don't necessarily know exactly what the angle is. All right, here we have the reciprocal and quotient entities. They're pretty straightforward. Cosecant is 1 over y, right? We know that, that's the definition, and of course sine is y. So it's the same thing as saying cosecant is 1 over sine. And by the same logic, secant is 1 over cosine, cotangent is 1 over tangent. Tangent is y over x. That's once again, our unit circle definition. And once again, y is sine, and in the unit circle, x is cosine. So tangent is sine over cosine. And then cotangent, it's just the reciprocal of that, cosine over sine. So we have all these identities that we can use to sort of play around with and use them to sort of alter expressions that we have to make them easier to calculate in some cases. On this next page, we have a really important identity called the Pythagorean identity, right? And the proof of this, first of all, this is the Pythagorean identity that cosine squared plus sine squared equals 1. But it comes from the fact that we're in the unit circle here. And the equation of a unit circle, which is a circle of radius 1, based around the origin, is x squared plus y squared equals 1. And once again, in the unit circle, x is cosine and y is sine. And so there we go, cosine squared plus sine squared equals 1. Now, the notation we usually use, instead of saying cosine inside parentheses and squaring it, we just say cosine squared theta and sine squared theta. It's easier to write it that way. So if you see this, it just means the same as this. Now, if we go ahead here, we can get these other two identities, which are also called the Pythagorean identities as well. They're sort of the secondary ones. If we take this equation right here and we divide the whole thing by cosine, like I did right here, well, cosine squared divided by cosine is 1. Sine squared divided by cosine squared, that's just tangent squared, right? Sine over cosine. And 1 over cosine squared is just secant squared. 1 over cosine is secant, right? And then for this other one, we divide the whole thing by sine squared, and we get cosine squared over sine squared is cotangent. Cosine over sine is cotangent. This is just 1, of course. And then 1 over sine is cosecant, so 1 over sine squared is cosecant squared. And so we have these two other Pythagorean identities that we can use as well. These will come up later on. All right, so let's look at some examples here. Let's say if sine theta is equal to square root of 5 over 5 and cosine theta is equal to 2 square root of 5 over 5, find the exact values of the remaining 4 trig functions. So go ahead and take a shot at that one. Okay, so if we know that sine theta is equal to square root of 5 over 5 and cosine theta is equal to 2 square root of 5 over 5, we're going to find the rest of the remaining trig functions using the reciprocal and quotient identities, right? So secant theta is just going to be the reciprocal of cosine, 1 over cosine, which is just 5 over 2 square root of 5, which if we rationalize the denominator is 5 square root of 5 over 10, which is just square root of 5 over 2. Cosecant theta is going to be the reciprocal of sine theta, so 5 over square root of 5, which if I rationalize the denominator is 5 square root of 5 over 5, or just the square root of 5. Tangent theta is going to be, using the quotient identity, square root of 5 over 5 over 2 square root of 5 over 5. And so when I multiply by the reciprocal of 2 square root of 5 over 5, the 5's cancel, the square root of 5's cancel, I'm just left with 1/2. And that, of course, means that cotan theta, which is the reciprocal of tan, is just going to be 2. It's pretty easy to figure out the other trig functions if I have sine and cosine. Let's look at some other trig expressions that we want to find the exact value of without having to use a calculator. So why don't you go ahead and find the exact value of tan 20. And you're going to look at this and go, 20 degrees? I don't know 20 degrees. That's not a special angle, but the key are the identities. So find the exact value of that expression and the exact value of the next expression. Okay. So for this first one here, we have tan 20 minus sine 20 over cosine 20. Sine 20 over cosine 20 is equal to what? Tan 20. And so this really just equals 0. So even though we don't know what tan 20 degrees is, it doesn't matter. The next one, what's 1 over secant squared going to be the same as? Yep. So just if the reciprocal of, so if secant is equal to 1 over cosine, then cosine is equal to 1 over secant, right? If they're reciprocals of each other. So we get cosine squared of pi over 12. Right? And so we have sine squared plus cosine squared, which we know equals 1. Pythagorean identity. All right. Now, another important type of problem that we want to be able to do is if we're given the value of only one of the trigonometric functions and just the sine of another, can we go ahead and use what we know about the unit circle to figure out the rest of them? So instead of being given like 2 of the functions exactly what they are, what if I told you that sine theta was equal to 1/3 and cosine theta is less than 0, and I said go ahead and find the remaining 4 functions using that information right there. Well, that's going to be a little bit trickier than the last one we did where we were given both sine and cosine. So first of all, if sine is 1/3, positive 1/3, and cosine is negative, where is sine positive and cosine negative? What quadrant? What? Quadrant, cosine is x, and sine is y, so it's going to be quadrant 2, right? So our angle is going to look, the angle that theta is going to be something like this. Right here's theta. And so what we're going to do is we're going to make a reference triangle here. Right? And we know that sine theta, which is the y coordinate, is 1/3. Right? And in the unit circle, what is r always? It's a really bad looking unit circle, but r is always 1, right? So can we go ahead and can we find knowing what we know about this, can we find the x coordinate? What can we use?
Pythagorean theorem.
Yeah, we can say 1 squared has to equal 1/3 squared plus the x coordinate squared, right? And so we'll end up getting 1/9 equals 1 plus x squared. And so x squared ends up equaling 8/9, right? And so x, which has to be positive, because it's a length, is going to be the square root of 8/9, which is going to be, well, the square root of 9 is just 3, right? And the square root of 8 is 2 square root of 2. So x has to be 2 square root of 2 over 3. So that means that cosine theta is x, so that's what cosine theta has to be, except it has to be what? It's in the second quadrant, so should it be positive 2 square root of 2 over 3? Secant theta is just going to be the reciprocal of cosine, so it's going to be negative 3 over 2 square root of 2. When I rationalize my denominator, I'll end up getting negative 3 square root of 2 over 2, right?
4, wouldn't it be?
Oh, sorry, yes, 4, yep, thank you. Cosecant theta is going to be the reciprocal of sine theta, which is going to be 3. Tan theta is going to be sine over cosine, so 1/3 divided by 2 square root of 3 over 3. So the square root of 3, or the 3's cancel, leaving us 1 over 2 square root of 3. Rationalize the denominator, you get square root of 3 over 6. So cotan theta will then be 6 over square root of 3, the reciprocal, which when I rationalize the denominator is 6 square root of 3 over 3, which is just 2 square root of 3. Oh, and tangent, sorry, should be negative, right? Because cosine's negative. And so is cotangent then at that point. So getting the signs right is just as important as actually getting the values right, it turns out. It's really important to know which sign, you know, depending on which quadrant you're in, what sign is cosine and what sign is sine. And the rest of the trig functions for that matter. All right, I'm going to give... So given that tan theta is equal to 1/2 and sine theta is less than 0, find the remaining trig functions. So if tan theta is equal to 1/2, what we can do here is, and oh, first of all, tan is positive and sine is negative. So what quadrant do we need to be in? 1? Sine's got to be negative. Sine is the y coordinate, right? So it's got to be either 3 or 4. And tan's positive, so it's got to be 3, right? So it's got to be quadrant 3. Because that's the only quadrant that tan is positive and sine's negative in. So there's our theta. Here is our unit circle. And so find the remaining trig functions. Let's go ahead and we know tan is 1/2. So let's assume that if tan is 1/2, that x is equal to 1, sorry, that y is equal to 1 and x is equal to 2. So y is equal to 1 and x is equal to 2, so we want to know what r is equal to. Whoops. So 1 squared plus 2 squared by Pythagorean theorem has to equal r squared. And so we'll end up with that r is equal to, so essentially we're assuming it's not a unit circle, because if we don't know we know that for tan theta, we know that x and y are in a ratio of 1 to 2, but that doesn't necessarily mean that r is equal to 1 in that case. So we can't assume that that's going to be the case. So we're going to have to use our definitions for the trig functions that involve r instead of just the unit circle. So we learned those the other day. We'll take those out. And so r is going to be equal to the square root of 5, right? The square root of 5. So we're going to have to use all of those definitions. So sine theta is going to be equal to, oh, and sorry, we're going to be in the, so they're both negative. So sine theta is going to be -1, which is the y coordinate, right? Cosine theta is going to be -2. Oh, I'm sorry, I'm not using the right definitions here. Because r is not 1, we can't use the unit circle definition, so we have to use the other definition. So it's going to be y, sine is, remember, y over r, x, cosine is x over r, and so forth. So sine is going to be -1 over square root of 5, the radius, which if we rationalize the denominator is square root of 5 over 5. Cosine theta is going to be also -2 over 5, so when I rationalize the denominator, it's going to be -2 square root of 5 over 5. Secant theta is going to be equal to the reciprocal, right? So it's going to be, secant theta is just going to be the reciprocal of cosine, which will be negative square root of 5 over 2. Don't have to rationalize the denominator. Cosecant theta is going to be negative square root of 5. And cotangent is the reciprocal of tangent. It's just going to be 2. So anytime we end up in a situation like that where we're given tangent, we assume that x is the numerator and y is the denominator, but that's probably going to give us a circle that doesn't have a radius of 1, so we need to find that radius, and then we can't use the unit circle definitions if we don't actually have a unit circle. R isn't 1, so it's not a unit circle, so we have to use the other ones, the x over r, the y over r, for a circle of radius other than 1. All right, let's look at one last. Some of these functions are even and some are odd. So these are the last of the identities that we'll see today. So see, we have our function here, right? And let's say we have an angle of theta and an angle of negative theta. So theta and negative theta. All right, and so if I open up an angle theta, let's say I end up at the point xy. Now, based on what we know about geometry, if I open up to negative theta, what point will I end up at? X negative y, yes, exactly. So, sine theta is going to be equal to, and we're going to assume this is the unit circle, not a circle of radius r. So sine theta is going to be equal to y. What's sine of negative theta going to be equal to? Negative y, right? So we're saying that they're opposites of each other, so sine of the opposite of theta is equal to negative sine theta. So sine is an odd function, and we're going to assume that its graph will have symmetry about the origin. Now on the other hand, cosine theta is equal to x, and cosine of negative theta is also equal to x. So we're saying that cosine of negative theta equals cosine theta, right? So cosine is an even function, right? And so that means cosecant of negative theta is just 1 over sine negative theta, which is just going to be equal to 1 over negative sine theta by that, and so negative cosecant theta. So cosecant theta is odd because it's based on an odd function, sine, and the same thing's going to be true, and I could do this proof, but I don't have room, so I'm just going to do it. For secant. Secant negative theta, if we did the same type of proof, would be equal to secant theta because it's based on cosine, which is even. So secant is even. So far, sine is odd, cosine is even, secant is even, and cosecant is odd. Look at tangent. So what's tan of negative theta going to be equal to? Well, let's use the quotient identity. What's tan equal to in terms of sine and cosine? Sine over cosine? What's sine of negative theta equal to?
Negative sine theta.
And cosine negative theta is?
Cosine theta.
So tangent is odd. And cotangent, whoops, is just equal to 1 over tangent negative theta, which is 1 over negative tan theta, which goes back to being negative cotan theta, and so cotan is also odd. So sine is odd, which means that cosecant is odd. Cosine is even, which means that secant is even, and tan and cotan are both odd. So these functions all have symmetry of some sort, which is going to lend them a whole bunch of different properties. And so that will come up in the homework tonight. All right, so that's good. Let me go ahead. I'm going to copy the homework and give that to you, and then that'll be that. So this is the homework for tonight. Comes from the handout that I emailed out to everyone today. Once again, the solutions to the odd questions are on the last page so that you can check your answers. Have a great day, everyone.